So folks, now that we've given the definition of a critical number, which is where both the partial derivatives are zero or where one of the partial derivatives doesn't exist, let's go ahead and find the critical numbers for a function like this. Folks, because we're going to eventually be plugging values into this function, I've given it to you in factored form. But if we want to go ahead and compute the partial derivatives, and actually for the solving that we want to do, it may be easier to go ahead and rewrite this. So let me go ahead and do so. We've got f of xy, and foiling that out would give us xy times, and then xy plus 3x minus 2y minus 6. Continuing to FOIL out gives us xy quantity squared plus 3x squared y minus 2xy squared minus 6xy. So now let's go ahead and compute the partial derivatives here. So we get f sub x would be 2xy. Let's say that's 2x squared y squared, excuse me. And then we would have plus 6xy, and then minus 2y squared, and then minus 6y. So there's partial f's of x. And then let's go ahead and compute partial f's of y. So again, treating the x as a variable, we would get 2 times the quantity xy, but then another factor of x, so that gives me 2x squared y plus 3x squared minus 4xy minus 6x. Okay, now we want to look at, notice that first of all, I guess we should say that the partial derivatives are defined everywhere. So although this is a condition that we're looking for, in this case it does not apply, since our partials exist everywhere. That is, the gradient will never be undefined. But now let's go ahead and look at where both of these are simultaneously zero. So let's set f sub x equal to 0, and let's set f sub y equal to 0. And if we do so, then we've got a sequence of equations we're going to solve. Before I go any further, folks, I want to tell you this, that there is no single strategy for finding these zeros. There is no single strategy for finding critical numbers. And the reason why is because typically we're solving what's called a nonlinear equation, and there isn't a single strategy for that like there is for linear equations. You will often try some substitution techniques. You got to see some examples in the My Math Lab for this, and I'm going to show you some additional examples here. In this case, actually both of these functions factor, which is rarely true, and it will greatly simplify when we factor them. So this is a very cooked up example. Let's go ahead and take a look here. Notice that I could go ahead and from each of the first two terms, let's grab this term right here, and oops, that should have been blue. Let's grab this term right here and this term right here. From the two of those, I could factor out a 2x squared. So if I did that, or 2y squared. So if I did that, I'd be left with simply x minus 2. And then if I group together these two terms, from each of those, I could factor out a 6y. So let's factor that out. If I factor out that 6y, I'd have plus 6y times x minus 1. And by the way, folks, I have an error here. Let's catch that up. That should have been minus 1 there, equals 0. Continuing to factor, I can rewrite this then as 2y times the quantity, factoring out a y, plus 3 times x minus 1 equals 0. And we see that the partial derivative with respect to x will be 0 if y equals 0, if y equals negative 3, or if x equals 1. Those are all values that would make that derivative 0. Again, folks, we won't always be able to find values just so simply when we work through this. Okay. Looking at this expression here, I'm going to again try that factoring trick, and let's group together, let's see, these have x squared, so let's group together those two terms. So we could factor out a x squared, I guess. And if we factor out an x squared, we'd be left with 2y plus 3. And from here, from these two terms, I can factor out a, let's go with a minus 2x. So if I do that, that's minus 2x times the quantity 2y plus 3, and we've set this equal to 0. And if we continue to factor here, I think I can write that as x times x minus 2 times 2y plus 3 equals 0. And so this gives us its own values that we could pick. But we're just going to take the zeros of this first expression here, and let's plug each of these into the equation f sub y equals 0. Again, folks, there is not a single strategy that will work for this. This strategy happens to work for this problem here, and I would argue that it's a very cooked up problem, and you just need to practice some algebra skills, some trial and error, try some substitutions, try solving for kind of a common expression in both equations, something like that, to try to find these solutions. All right, so if we plug each of these, let's go ahead and pick y equals 0. We plug that into f sub y. If I plug y equals 0 into that, that would leave me with x times x minus 2, 2 times 0 plus 3 equals 0, or just 3x times x minus 2 equals 0. So that happens if x equals 0 or if x equals 2. So y has to be 0, but if for the first equation to be 0, but if y is 0, then that would force x to be 0 or x to be 2 in the second equation, and so then we would get these two critical numbers, 0, 0, and 2 comma 0. Those are critical numbers. So let's just put therefore. By the way, just to clarify, there's the 0 that we let y be in that problem there, and then we had this 0 that was x, is this 0 here. Okay, so that was if y were 0. Let's go ahead and pick y equal to minus 3. Again, for this first equation to be 0, we need y to be minus 3 or 0 or x to be 1, but picking y to be minus 3 to force the first one. But if that were the case, what would that give me in the second equation? And then let's force that second equation to be 0. So if we did that, we would have x times x minus 2 times the quantity 2 times negative 3 plus 3 needs to equal 0. So it gives me minus 3 times x minus 2 has to equal 0, which gives me x equals 0, or x is equal to 2 again. And so that gives us the critical numbers 0 comma minus 3 and the critical number 2 comma minus 3. Those are critical numbers. Finally, let's pick the last one. Let's pick that the partial derivative of f with respect to x is 0 when x is 1. So if we pick x equal to 1 and we plug it into the first into the other equation that we want to set equal to 0, we would have 1 times 1 minus 2 times 2y plus 3 would have to equal 0, which happens when minus 1 times 2y plus 3 is equal to 0, or when y is equal to minus 3 halves. And so this gives us the critical number, the single critical number 1 comma minus 3 halves. There it is, folks. We found the critical numbers for this particular multivariable function. As a reminder, folks, this trick worked for this problem where it was easy to factor. That will not be the case for all of your questions, and you just need to show a little bit of flexibility with that. Now, if you have any questions, feel free to come by and see me, and I'd be happy to go through some strategies with you, but you will also get to see these strategies when you work through my math lab. The last thing, now that we've got those critical numbers, the last thing I ask you to do in this problem is just find all partial derivatives, and that's really just to save some space because we're going to need that on the next page. So if we were to, we've already computed f sub x, so we could compute f sub x. Remember that says take the partial derivative with respect to x, again with respect to x, using this different notation than we sometimes use. So if I do that, let's see here, taking the partial derivative of the first term, again with respect to x, will give me 2y squared. Taking the partial derivative of the second term, again with respect to x, would give me plus 6y. And the other two terms are constant as far as x is concerned. We could also calculate this mixed partial here, f of xy. So as a reminder, that is f sub x, and then we take the partial derivative of it with respect to y. So what would we do here? We would take this partial derivative, taking that now with respect to y as a partial derivative would be 4xy plus 6x minus 4y minus 6. Now we need to take the other two partials, second partials, when we take with respect to y first. So we'd have f sub y, y. Let's do that. Remember that says take the partial derivative with respect to y. That's this right here. And take the derivative with respect to y again. And so in this case we would get oops, I'm sorry, that's not true. We would get 2x squared. And that term is constant as far as y is concerned. And we'd get a minus 4y, and that term's constant. So there's our partial derivative, our second partial, when we take it with respect to y both times. Finally, let's go ahead and compute f sub y x. Remember that says take the partial derivative with respect to y with respect to x. Now, folks, do I actually need to complete this one? And the answer is no, because all of these partials are coming out to be continuous. By Clairaut's theorem, this second mixed partial is equal to this second mixed partial. And there's no, you could just go ahead and copy this down. What I actually like to do, folks, is even though I know that these two expressions, this one and this one, they're going to be equal, I actually like to take the partial derivative of y with respect to x again, just as a check. It helps me check to make sure I haven't made any glaring errors as I've been working through some of these partials. So if I take the partial derivative of this with respect to x, notice that I will get, for the first term, I would get 4xy. With respect to x, that would give me plus 6x. With respect to x would give me minus 4y. And with respect to x would give me minus 6. And notice, yep, sure enough, those two agree through the wonderful theorem that is Clairaut's theorem. So folks, on the next page, we will talk about how to actually perform our second derivative test, but this was just the process of finding the critical numbers, which we did in the first part of this video. Thanks, I hope that was helpful.